Good morning. My name is Elizabeth Wallace. I'm from Greenwich High School, and today I'll be sharing with you my work, the controlled delivery of sulfoxaflor pesticide via a cinnamaldehyde-infused hydrogel to reduce toxicity to honey and wild bee pollinators. Ever since the use of synthetic pesticides in agriculture has become a widespread practice, agricultural yields have increased, as well as product quality. As a result, we rely heavily on pesticides to feed our growing population. However, many pesticides are not targeted, killing all insects that come into its path, including beneficial insects. In fact, according to a paper written by Tay et al. In 2020, of 3.5 million tons of pesticides applied annually, less than 1% are consumed by or come in contact with target pests. This leaves the residual 99.9% of pesticides to move into the environment. The implications of this are massive, and one that is especially concerning is how this contamination affects bees. Pesticides can have adverse effects on bees' ability to reproduce, navigate, and pollinate, and can even kill them. If we continue to apply pesticides in large amounts without beneficial insects in mind, it will be devastating for bee pollinators and for society, which relies on bee pollinators for 1/3 of the food we eat. As a result, hydrogel application has been identified as a different avenue of pesticide application. Hydrogels have been shown to improve use efficiency and therefore protect the environment. Before I introduce you to the hydrogel I created, I would like to first describe the two chemicals I used throughout experimentation. Sulfoxaflor, or S, is an insecticide developed to target sap-feeding insects that have been gaining resistance to commonly used insecticides. Sulfoxaflor has been shown to be harmful to bees, and in 2019 had restrictions lifted on its applications. Cinnamaldehyde, the chemical which gives cinnamon its color and flavor, is a natural bee deterrent that exhibits low toxicity. So my goal was to develop a gel-based encapsulation system to time-release sulfoxaflor for intended pesticide function while also releasing cinnamaldehyde, which will act as a natural scent repellent for bee pollinators. Hence, the sulfoxaflor cinnamaldehyde hydrogel, or the SCH gel, was developed. As portrayed by this diagram, sulfoxaflor is incorporated into a chitosan alginate hydrogel complex and coated with cinnamaldehyde. Theoretically, the SCH gel should first be activated by typical irrigation, initiating the outgassing of cinnamaldehyde and the controlled release of sulfoxaflor into the soil to be absorbed by the treated flowering plant. The first step was fabrication of the SCH gel. Methodology from a paper written by Yang et al. Was modified to create three variations of the H gel. First, a blank hydrogel without sulfoxaflor or cinnamaldehyde, which you can see on the bottom left, followed by the sulfoxaflor hydrogel with just sulfoxaflor, which you can see in the middle, and finally the SCH gel, which had a coating of cinnamaldehyde, which you can see on the bottom right. I then went to confirm that the fabrication had been successful, and to do this, I used ATR-FTR spectroscopy with wave number on the x-axis and percent transmittance on the y-axis. As you can see from these three spectra, which show sulfoxaflor alone, the hydrogel alone, and finally the sulfoxaflor in the alginate hydrogel, the sulfoxaflor was successfully incorporated, which you can see with the presence of the new spectral peak. I then wanted to confirm that cinnamaldehyde had been successfully incorporated as a coating. To do this, I took spectra of the sulfoxaflor, hydrogel, cinnamaldehyde, and finally the SCH gel. As you can see here with the circle, the final SCH gel had a successful incorporation of the cinnamaldehyde. To provide further proof that the SCH gel was fabricated successfully, a freeze-dried sample was then examined via SEM, providing compelling evidence of the porous outer shell of the H gel, which should be conducive to swelling and dissolution. The pores were found to be 10 to 15 micrometers in size. Before analyzing the release of sulfoxaflor from the hydrogel, I needed to calibrate detection of sulfoxaflor within the context I intended to use it. To do this, I first created quantities of sulfoxaflor equivalent to approximately 10 SCH gels and dissolved them in water, followed by the addition of methanol. After stirring, I dried these solutions on FTR crystal to produce an FTR spectrum. As you can see here, the size of the spectral peak decreases with decreasing concentrations. I then took the peak area of each peak and produced the resulting calibration with sulfoxaflor mass on the x-axis and peak area on the y-axis. Similarly, I created a method to examine the dissolution of sulfoxaflor from the SCH gel. To mimic field pesticide application, 2, 4, 6, 8, and 10 SCH gels were placed individually into 10 ml containers with 0.5 grams of moistened sawdust. After heating at 32 degrees Celsius to mimic an average summer day, the containers were centrifuged and vigorously stirred. The samples were then dried on ATR-FTR and the spectra was taken. You may be wondering why I decided to use sawdust instead of soil. Well, sawdust is composed primarily of cellulose, which has a spectral peak that does not coincide with the sulfoxaflor peak, therefore making it much easier to identify the sulfoxaflor. The results from this experimentation are reported by this table, which shows the sulfoxaflor mass released and detected versus the actual sulfoxaflor load in the same SCH gels and the corresponding percent release efficiency. It was found that 10 SCH gels demonstrated approximately an 83% release efficiency, whereas 2 sulfoxaflor cinnamaldehyde hydrogels demonstrated a 95% release efficiency. This indicated that a higher water per SCH gel availability corresponds to the increased release of sulfoxaflor. This graphical interpretation on the right shows SCH gel quantity on the x-axis and sulfoxaflor mass on the y-axis, and this shows the difference between the sulfoxaflor mass released and detected and actual S mass. You can see that they are very close, indicating the SCH gel is efficient in releasing sulfoxaflor. However, I still noticed there was a gap, and in order to determine if this was due to the SCH gel itself or the method of recovery from sawdust, I designed a new experimentation. To do this, I created separate samples of sulfoxaflor in 0.5 grams of moistened sawdust. After heating and methanol was added, vigorous stirring and centrifuging, FTR spectra was used to calculate the peak area. From this experimentation, the results indicated an approximately an 86% recovery efficiency of the extraction and detection of sulfoxaflor from the moist sawdust. The release of the efficiency of the SCH gel can therefore be corrected to a release projection of approximately 96% efficiency for the 10 SCH gel application. The graphical interpretation on the right shows the new improved SCH gel release efficiency with percent recovery in the green. You can see the change in the release efficiency from the red to the green attributed to the shortcomings of the recovery method. Now that the release of sulfoxaflor had been confirmed, the next step was to analyze outgassing of cinnamaldehyde. To do this, a gas chromatographic method was established with flame ionization detection, or GCFID. I found that the retention time was 26.5 minutes at these conditions. As you can see, the x-axis is the time and the y-axis is the responses. From this data, I created this calibration standards of peak area versus micrograms of cinnamaldehyde. To model outgassing of cinnamaldehyde, a model similar to the measurement of release of sulfoxaflor into solid was designed. 4, 6, and 8 SCH gels were placed in 10 ml containers with 0.5 grams of moistened sawdust, and after being heated, the resulting gas in the headspace was extracted and analyzed via GCFID. The resulting peaks are portrayed on the right. The GCFID measurement found that approximately a 20% release of cinnamaldehyde from the SCH gels had occurred in 24 hours. In addition, it was found that the release of 1.59 mg by 8 SCH gels is well under the mg LC50 of 7.9. The LC50 is the lethal concentration 50. As you can see on the graph to the right, there is a large gap between the amount of cinnamaldehyde released by 8 hydrogels versus the LC50, indicating that the SCH gels are safe for bees and will act as a deterrent without harming them. From this data, I was also able to conclude that as many as 32 SCH gels can be employed beneath a plant, producing a 6.4 mg cinnamaldehyde release before this begins to border the LC50 of 7.9 mg. Finally, I wanted to identify the amount of hydrogels that would be needed to employ under an average flowering plant based on the typical application of sulfoxaflor. Based on the transform label rates, the commercial chemical that contains sulfoxaflor, 4 SCH shells must be used to reach the suggested application amount. This corresponds to the release of 0.81 mg of cinnamaldehyde, which is far below the 7.9 mg LC50.
2 minutes.
In conclusion, I was able to create a hydrogel that had a 96% efficiency in releasing sulfoxaflor, which provide compelling evidence that it is very similar to the release rate of delivery of sulfoxaflor alone. In addition, I was able to find that SDH gels outgas cinnamaldehyde at a rate of approximately 20% in 24 hours, and this would indicate a 5-day duration if a linear release model was assumed. I was also able to find, based on commercial rates, that 4 SDH shells are needed to effectively treat a plant, and this corresponds to a 0.81 mg release of cinnamaldehyde, which is far below the 7.9 LC50. I would also like to point out that this hydrogel takes into consideration honey and wild bee pollinators. Native bee pollinators are often left out of consideration when considering if insecticides are safe for bees, and cinnamaldehyde is able to deter both bee pollinators and native bee pollinators. In the future, I would like to determine the longevity of the cinnamaldehyde release from the SCH gel, as I did not have as many samples as I have liked to in the cinnamaldehyde release studies. In addition, I would like to investigate the direct application of the SCH gel on bee pollinators, and as I was unable to do that in this research. And in addition, I would like to do future research on the uptake of sulfoxaflor in order to confirm that the SCH gel is able to efficiently release sulfoxaflor. I would like to thank Mr. Bramonti for his help throughout this research, as well as Mike Loso from Dow Agrosciences. And lastly, I would like to thank CT-JSHS for this opportunity to present my research. Thank you, and if you have any questions.